Unit 5, Ionic Compounds, Chapter 3. This part of the unit takes us into some of the math portions of it. We do go through a number of examples. That's why this chapter takes a little bit more time notes-wise. Not a lot of length of notes. It's actually more computations shown as examples so that you have something to look at and see how to do some of these. Remember back in Unit 3, we talked about atomic masses and their relative mass to one atom of carbon-12, which we then assigned a 12 AMU. And then again in this class, to make our calculations easy, we're going to use whole numbers so that everything fits up nice. The formula mass is the mass of one formula unit of a compound. Now that means it's the sum, and that's what that little E here means. It actually is a summation. That's a math symbol to mean summation of all the atomic masses in a formula unit. How do you find that? Well, you find how many of each element are present, and you multiply it by its specific atomic mass and add them up. I do them a little bit differently as the formula here suggests, but the method in which I use does work fairly well, and usually will be is easy for students to understand. And that ultimately is what we want and is the most important part of it all. So what is the formula mass of, say, a compound called sodium chloride, NaCl? Well, we need to look at this compound specifically, Na and Cl, and to do that, what we do, we start off by writing Na and Cl. I count how many of each I have, and I see that I have one sodium and one chlorine. From there, I can go through and start to see that on my periodic table, the mass of one sodium is about 22.9 something. Well, for us, we're going to use 23. And for chlorine, we see that it's 35.45. But for us, we're going to just use it at 35. Now, easily to see is that 1 times 23 is just 23. And 1 times 35 is 35. We add those up, so 3 plus 5 is 8, and 2 plus 3 is 5. And that gives us the atomic mass of 58 AMU, or what I prefer is 58 grams per mole. In the next example, we see that we don't have the formula given to us, and therefore we actually have to figure that out. Now again, this is where naming was such a big important part of it. Is you have to look at and make sure that you're naming things correctly. And so when we look at the naming, we can see that iron 3 nitrate. Now why is that 3 there? Well, it indicates to us that we are using iron 3, meaning iron will have a positive 3 charge. And so we have to indicate that. Nitrate, if I look on the back of my periodic table, is labeled with NO3 with a negative 1 charge. And those charges don't match up, so we do what we've been doing. That's the crisscross method. To give us the formula of FeNO3 3, with the 3 outside in the parentheses. Does that change how we do our formula mass? No, not at all. And what we do is we just calculate out our iron, our nitrogen, and our oxygen. Now when I look at and see how many iron do I have just 1, because I look at the formula and I see that I have only 1 iron. When I look at nitrogen, I can see and distribute that 3 to the nitrogen, and therefore I have 3. And now 3 times 3, because I have to distribute that 3 on the outside of the parentheses to everything inside, I have 3 times 3 is 9. Now when I look on my periodic table, I find that the atomic mass of iron is 56 approximately. Nitrogen is 14. Oxygen is 16. Doing the math that I need to accomplish this, 56, then 3 times 14 should be 42, and 9 times 16 is 144. I add all of those up to get my answer of 242. And again, I'm going to use the one that I prefer, grams per mole. And we would use this when we get into Unit 7, is using the grams per mole a little bit more frequently. The next example, what is the formula mass of vanadium 5 sulfate? Well, nothing has changed in that we still find out V, and sulfur, and an oxygen. How many vanadium do I have? I have 2. I know because there's a 2 right there. Sulfur, I have 5. And oxygen, this time, I got a boatload, and that's 20. I need to look on my periodic table to find vanadium and see that it's very close to 51. Sulfur is about 32, and oxygen, again, is 16. Now, upon conclusion of this, you might actually start to remember or have memorized some of these elements as we write them in their formula masses, and that's okay. There's nothing weird with that. Now 5 times 32, I'm going to just use my calculator here. And for 20 times 16, I might be able to do that one in my head, but for verification, not a bad idea to make sure that I did it correctly to get 320. Adding them all up together, I can see that I have about 582 grams per mole. So formula mass isn't hard. What can make things difficult is if you don't know your naming yet. Now, why is this important? Well, when we go into the lab, we're not going to actually make certain measurements based on, how many formula units do you need? No, if you go into the lab, you actually can't measure out formula units in that manner. Instead, you need to measure out grams or volume. Well, to do that, to measure out grams or volume, and to know how much of everything that you have there, such as like a recipe, you need to say, how many of each one and how much do you weigh of each one. So there's a little bit of what we'll be doing is doing some converting, so that we can figure out what and how much of everything we're actually measuring. Because the numbers that we're dealing with, and why I prefer to use molar mass, is because the number that we're dealing with, the atomic mass, can also goes by the name or definition of molar mass. The molar mass tells us, and is, again, as you can see here, the labeling is done just a little bit different. Again, the grams per mole. But the important part of this is that we have what is that molar mass actually doing? Well, it's telling us how many atoms or how many of each element. It's very down to the atoms, how many of each one we have. And so what we start to do is bring in this idea of the mole. And so if we do that, we have this idea of the mole, we'll be able to understand some parts of that. So if we weigh out 12.01 grams of carbon, we would have what is the equivalent of 1 mole of carbon. 1 mole of carbon is 6.02 times 10 to the 23rd atoms, or formula units, or molecules. That being said, if we measured out 241.88 grams of iron 3 nitrate, that would be the exact mass that we would have for 1 mole of iron 3 nitrate, meaning that we would have a total of 6.02 times 10 to the 23rd formula units of iron 3 nitrate. This is all because of the mole. The mole is also known as the chemist's best friend. Is that when we begin Unit 7, we'll see that we will be converting in and out of the mole. We'll do some of that in this unit, but we really get down and dirty in it in Unit 7. A mole of hydrogen gas contains 6.02 times 10 to the 23rd. The atomic mass of fluorine, 19 AMU. So the molar mass is calculate the molar mass of ammonium nitrate. This might take some time. Now, what do we do with that? Well, we convert between mass, moles, and the number of particles. Number of particles is the atoms, formula units, whatever it have you. Now, if you remember back, Na is equal to Avogadro's number, which is again the 6.02 times 10 to the 23rd atoms, particles, formula units, molecules, whatever it have you. Now, being able to look at what we have here is that we can see that there are a number of different things that will be measured here. You can start on any one direction of here. You can start in the middle with moles and convert any direction from that. Now, when you are finding that we have this, it is a flowchart that helps us understand, or it takes maybe some of the algebra out of it. And that's what some students do, is they have such an issue with algebra that having this, it takes a lot of this idea out. And so when we start from mass and we need to go and convert 2 moles, we can see that the divide sign, or the backslash, and we divide by the molar mass. If we started at moles and needed to go convert to the mass, we would multiply by the molar mass. If I started with the number of particles and I needed to convert to the number of moles, I would divide by Avogadro's number. If I started with the number of moles and needed to know how many particles or formula units or atoms, I would multiply by Avogadro's number. And if I started on one side, such as mass, and needed to convert to particles, I can see that there's no direct line. There's not a direct line that takes me from one to the other. The only way to do this is to go from mass to moles, from moles to particles, or formula units, or atoms, or whatever it may be that you're solving for. So you cannot go direct one way to the other. You have to go through the mole. You have to convert the mole. That is why it is a chemist's best friend. In the first example we have here, we see that we're given the molar mass of sodium chloride. A little bit more exact than maybe we had calculated earlier. But regardless, how we do it is this exactly the same way. Now the molar mass of sodium chloride is that. How many moles are in 5 grams? Well, this is just like a conversion problem. And in conversion problems, we need to find out what we're given. And in this case, we're given 5 grams. What do I want is moles. So I start with my given, 5 grams of sodium chloride. And to get rid of that, or to do that, if I looked back at my notes and saw that I wrote down that to do this, I need to divide by my molar mass. Divide means down, or denominator, meaning the number, the molar mass of the number 58.44 goes on the bottom. Divide down. The mole goes on top. Now, when we do it this way, we can see that from an algebraic point of view, the grams will cancel out, leaving us with what we want, and what we want is moles as our label. Well, I need to now look at my division here, and it's taking 5 divided by, divide means down, that, and we see that I have a fairly small number of moles of 0.08, and I'm going to round it to 6. My label, which is the other part of my answer, is moles NaCl. Now in the next one, we don't have all the information given to us. So how much calcium fluoride should you weigh out if you want 0.5 moles? We're going to be having to calculate some things here. And so what I need is the molar mass of calcium fluoride. Well, we went over how to calculate the molar mass, which wasn't too hard. And I can see that I have 1 calcium and I have 2 fluorine. On my periodic table, I can see that the atomic mass of calcium is 40. The atomic mass of fluorine is 19. Doing the basic computations, I can see that I have 40 plus 38. There's something on my iPad here to give me 78. Again, grams per mole. From there, now I have what I need. And I'm going to underline, what am I given? and I want how much should I weigh out. Probably saying grams. Well, that's one of the only places I could go. So I start with what I'm given, because it's a conversion problem. And I start with 0.5 moles of calcium fluoride. Now from there, I need to figure out, okay, and now I have to multiply when I'm converting. I multiply what I know by my molar mass That one did not look good whatsoever. And so I now can see from an algebraic point of view that my mole canceled out, leaving me with grams, exactly what I can weigh out. And so I need to take and multiply 0.5 times 78 to give me 39 grams. Grams of what? Well, that is calcium fluoride. Now we're going to go another one where I have 9 grams of water. How many moles do I have? Well, I need to go through and calculate again. Let's use blue for water again. Calculate the molar mass of water. Gives me 2 hydrogen, 1 oxygen. Looking on my periodic table, I'll see that hydrogen is 1, oxygen is 16, giving me a molar mass of 18. Well, if I see what I underline, what I'm given, and what I want, I can see that I need to, again, just like all conversion problems, I need to start with what I'm given, convert to what I need to, and in this case it's a direct conversion. In some cases I might have to go multiple steps, so I have to kind of go one to the next. But here I can go directly. But now when I'm converting from mass to moles, I need to divide, and divide means down. And that's so my grams cancel out. And I can see that my grams cancel out, leaving me with just moles. Well, moles of what though? I should probably have that in there. That would be of water, not O2. And so now we can just do my division in my calculator and see that I have 0.5 moles of H2O. Now, if the reaction calls for 0.01 moles of hydrochloric acid, how many grams do you need? No, that's telling me that I want grams. How many grams? I'm given this many moles of hydrochloric acid. I need to calculate the number of the molar mass of hydrochloric acid. And because it's all 1 to 1, I can just very simply look and say, oh, look, it's just, instead of 1 times 1 and 1 times 35, I can add that up together because and say that it's about 36 grams per mole. And when I start, I got to start with what I'm given because it's just a conversion problem. Of HCl. Now, because I want mass, I need to multiply my molar mass and when I do that, we can see again the moles cancel out. And I need to multiply, by the way, that never gets old, and get the answer of what I want to be 0.36. Make that point a little bit more prevalent. Grams of hydrochloric acid. Well, what happens if we had asked the question of how many atoms? And it's not of He, it's of helium. And so, if I start with 4 grams of helium, how many atoms do I have? Well, to do this, I need to convert to moles, because if I remember back, I do not have a direct conversion between mass and the number of particles or the number of atoms. And so what I have to do is convert from grams to moles, from moles to atoms. Identify what I want and what I'm given, and start my conversion. Now one might ask, why did you not calculate the molar mass of helium? Well, if I know if helium is just it, I just have to look on the periodic table to see that the molar mass of helium is 4. And because I'm converting between grams to moles, I need to divide and therefore divide down. Now that I have my label in moles, I can convert from moles to the number of atoms. Now you have some options. You could do this calculation right here and hit enter in your calculator and then continue further on. Excuse me. I am a little bit more of a traditional and prefer to continue right along in this second part of the conversion. And from here, I need to take and convert Avogadro's number. And I need to use 6.02 times 10 to the 23rd. And in this case, it will be atoms. Over 1 mole. And when I do this, I can see that, again, my moles cancel, leaving me with atoms. Now I can punch all of that into my calculator, and if we do punch that into our calculator, be sure to punch the times 10 to the 23rd into your calculator correctly. If you do it incorrectly, you will find that some numbers are not going to play nicely. And I will find that ultimately 4 grams of helium is equivalent to 6.02 times 10 to the 23rd atoms of helium. Because 4 divided by 4 is 1, and 1 mole of anything is 6.02 times 10 to the 23rd atoms. The next one, we're going the other way, and we're asked to find how many grams if I have this many molecules of nitrogen. So I now have to look at some things. I now need to calculate the molar mass of nitrogen. Now, what a lot of people will forget is that nitrogen is diatomic, meaning that nitrogen is seen as N2. That is a molecule, and that's kind of the key term there, is molecule of nitrogen. So I need to now have 2 times 14 to find the molar mass of nitrogen to be 28 grams per mole. I have to start with what I'm given, which is 2.34 times 10 to the 25th. In this case, it would be molecules of nitrogen. I need to, because I cannot convert directly to the number of moles, I need to use Avogadro's number. And 6.02 times 10 to the 23rd molecules is equivalent to 1 mole. Now that I have it in moles, I can see that I can calculate it to mass. Ultimately, what I want. From there, I need to multiply by the molar mass. And when I do that, 28 grams goes on top. The 1 mole goes on the bottom. My moles cancel out. Now when I punch this into my calculator, I need to be very careful about making sure that I punch this into my calculator correctly. If for some reason I do this incorrectly, I am going to get a very large number. And if you get a very large number, meaning something bigger than the number that you started with, you should double check your answer. Because if you had, especially with the exponent is larger, it would be somewhere around like times 10 to the 49th. And that's just weird. We don't need to get that far. And so we have an answer of 1,888. And I'll round it to 0.4. And that would be grams of nitrogen. If you forgot that nitrogen was diatomic, you would have got about 500, and that would tell me that you forgot that nitrogen was diatomic. But we know it's not, so we'd calculate it correctly. Calculate the number of moles in a spoonful of table sugar. Not that Mary Poppins knew what she was talking about. Having a mass of 10.5 grams. This might take some time. Calculate the mass in grams of a sample containing 1.85 times 10 to the 34th molecules of water. You're going to have to calculate the molar mass of water. Now, the resources that a lot of us find, or mining companies find, in the Earth's crust are drilled or covered in other ways. Strip mining is another one. This type of mining is known as ore. This is the natural rock that contains the metals and minerals that we need and have our value. This ore is not evenly distributed throughout the Earth, and it's not always cost effective to mine or drill for these certain resources. So we have to figure out, is it worth our effort to do such a thing? And so would have to do a cost analysis. Well, if we can do a percent composition, we might be able to determine whether or how much of a mineral contains a certain metal that we want, such as gold or copper or silver. and using current mining practices. And so that's where we're going to use and take the idea of percent composition. Copper, for example, could only be mined originally in ores that had about 35 to 90% copper, in which if they had less than that, it was not there. You almost had to see the copper vein in the rock formation. Now, those mines are, for the most part, tapped out. They're dried out, so to speak. They've been mined fully. Now, that doesn't mean that there isn't copper still present, and that copper still is present. It's just in the rock and mineral. It's in around those formations. Now, that means that we have to look at some things a little bit differently. And what we need to do was produce a metallic copper. Is 1% will work. This ability to mine these less than 1% mines comes from chemical processes, and some of them might be taken into some consideration depending on the impact to the environment. So some of them, because they are chemically done, they can have an effect on the environment. So some of those analyses are actually still continued. How does this done? Well, it's a percent composition. It's percent by mass of each of the element in a compound. So the element A would be the element in which you're under question, and the compound is the formula mass, or the molar mass of that compounds, or the molar mass. Well, that's kind of a really bad MM there. We have the molar mass of the compound and the molar mass of element A. You multiply that by 100 and it'll give you your percentage of element A. Now, using percent by mass can be helpful in figuring out how much could be extracted. Now, we're going to do some calculations that may or may not have that figured into as in the mining aspect of it, but the ability to make those measurements is still going to be done, and we will be looking at doing the percent by mass, and it would just be where could this be used, and that's what we would be looking for when doing these types of computations. Such as the example, sodium bromide. Now, we might want to have sodium specifically for any one specific reason. However, we're going to look and do our calculation. I'm going to need to do my calculation of the sodium bromide first, and because it's 1-to-1, I'm going to take a little bit of the easy way out and say that the atomic mass of sodium is 23. The atomic mass of bromine is, we'll go round up and say that it's 80. Add them together, we get 103. Now, what is the percentage of sodium? Well, we should know that it's going to be very close to about 23%, and that's giving us the evaluation part of our acing the problem ahead of time. And so we can see, but what we'll do is put it in the equation. So 23 divided by 103, and I can find that, and it's just like calculating the percentage on your test. You say you scored 23 out of 103. I would hope that it was better. And you would get a decimal of about 0.2233. And that's not very good if that was a test score, so I'm guessing it would be much higher, hopefully. We multiply that by 100, and we would get a percentage of sodium in sodium bromide of about 22.33%. Now, is that enough to mine? It would depend. It depends on what you're looking for. What is the percentage composition of sulfur in potassium sulfate? Same type of thing, where we have to calculate how much I have of each part, and I need to use it's worked there, but I don't like it. And so I need to calculate the formula mass for my compound. Potassium is 39. Where do I get that number? My periodic table. And 16 is for oxygen. Doing some calculations. This is where having a nice handy dandy calculator comes in handy. And we get 78, 32, and 4 times 16 is 64. I need to add all them up. To get 174. Now I need to worry about my sulfur, and so when I do the calculation, I need to take 32 divided by 174. And I can see that I get a pretty small decimal of about 0.184. I'm going to round that there. And I multiply that by 100. And my answer ends up being 18.4%. Decimal didn't show up very good. Now, say a new penny, post 1983, has a mass of about 2.5 grams, and has only 0.0625 grams of copper. What is the percentage of copper and zinc in the penny? To find the percent of copper, we need to find and use this, and it's not too hard. It's the same method, and we just don't need to know, because it's an alloy, we don't need to know the molar mass of everything. I just need that. And what we can see here is that we'll have the 0.0625 divided by my 2.5, and I'm going to get a very small number of 0.025. Multiply that by 100. Oop, not 1,000. Not 1,000. Only by 100. And I would get 2.5%. Well, now if I had 100% of a penny, I have two options in finding the amount of zinc. I know that I need 100% of a penny, and I can take and go 100 minus 2.5, And that would give me 97.5%. I can also subtract off, as another option, 2.5 minus 0.0625 and see that I have 2.4375 divided by 2.5, because that's the whole thing. That's how much this is how much zinc I have. I end up getting, if I multiply that by 100, 97.5%. So you have two different ways and sometimes to find that in there. The mineral produces more copper than sulfur. How much copper is extracted by this mineral? And so we need to find, in this case, we'll find the molar mass and when finding the molar mass, again, I need to look on my periodic table to discover that the atomic mass for copper is 63.5. So I'm going to err on the side of caution, and we're going to go 64 on that. And so I multiply that out, and I get 32 be 128. Add those together, 1, 5, there we go. And so I can now do my other division of 128 divided by 150. To give me 0.853, and that seems to be repeating. Times that by 100 to get 85.33% copper. Another mineral mined for copper is very complex. And here, what is the percentage of copper in this mineral? Much more complex. And this is how actually most minerals are written. And so their formula masses are calculated exactly the same way. They're just really complex. It comes into their ionic formulas, and that's why we didn't look at how ionic compounds look in their and how they are there. Ooh, almost made an example. One thing we need to notice that our oxygen here there's 5 of them because we distribute that out. So I'm going to change that 3 there to a 5. Almost made a mistake there. That would have been embarrassing. And so we have into hydrogen. Going through and finding these on my periodic table, or if you have them memorized, either or, it works for me. We do need to have them eventually figured out. I would suggest looking them up, calculating them all out. $12 and 128. Need to add all that up just like before. Just that there's going to be a little bit more numbers to crunch. So it is important that we make sure that we punch and keep everything accounted for, as I almost made a mistake as well. I find that I have about 222 grams per mole. I need to now look and do my computation. So 128 divided by 222 gives me about 0.57, and I'm going to say 7 again. Multiply that by 100, not 1,000. A little crazy on my numbers there. No, 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 no. Oh, whatever. And so we end up getting, let's scratch that out. Must have punched another button. So multiply that out, and we can get, hopefully you've seen this before, so 57 point, make that decimal a little bigger, 7%. So a little bit less. Well, there's a lot of other stuff in there as well. Calculate the percent by mass of carbon, a compound present in rotting meat, cadaverine. It might require a little bit more time. Well, that concludes Unit 5. The next unit, Unit 6, brings us through chemical reactions, everything that is involved with those. Hopefully you'll continue working on these and be able to reference this information for Unit 7, as we will be needing a lot of this information in Unit 7.